Hello everyone, this is Discrete Mathematics final project. The topic is music visualization. As you have seen on the intro video, the music visualization is just animated version of the music, and we were using LED strip to create our device. So let's see how we did it. As you can see here, we were using our microphone to record the real-time sound or audio. Then the Arduino Nano were running the CE code which was detecting the amplitude of the signal, and we're selecting the corresponding hue, saturation, and value of the LED to create the fade and just the pattern that we need. The materials that we were using: plus 5 voltage LED strip with 3 pinouts, Arduino Nano, microphone KY038, which is the most sensitive and cheapest microphone that you can buy for Arduino. The pinout for microphone: there are 4 pinouts, which is the digital signal, which we're not using in this project, plus voltage, ground, analog signal. LED strip with 3 pinouts, data input, plus 5 voltage, and ground. So here's the Arduino Nano pinout. I should only mention 3 categories which we were using: the power, the plus 5 voltage, which we're using as the power supply for our devices such as the microphone and LED, analog pins as the input, we're using A2 from the microphone, and output pins which we're using was the D4 to output the data into LED. This is schematics. As I said, the ground is connected to ground in both cases. Plus voltage is connected to plus voltage in Arduino. Data input is connected to D4, and analog signal is connected to A2.
So, how does our project actually work? Our project works heavily depends on the microprocessor inside of the Arduino Nano. So this microprocessor, the code for it is written in the Arduino integrated environment in the language C. So I'm going to show you the basics. As you can see on the graph, we take the inputs from the microphone, which are expressed in the voltage. Then we process it, and then we output it in the change of lights. So what functions do we use for that? So the first function we use for that is looking at the current difference between the average and the reading of the microphone, of the current reading of the microphone. You can see on the slides that we're taking the difference between the current reading of the microphone and the average, right? And then we take this difference and we scale it. We scale it from 0 to max to the amount of lamps we have, which is actually 60. So for example, the difference of 50 would scale to 20, and the 20 lamps would become a light. And so there is another function that we use, which is fade. So why do we need to use this function? Because we need to see the change in the lights. If you wouldn't use the fade function, the lamps would just stay alight all the time. So we use this function to show the next change. And this function is pretty nifty because of two things. It fades the lamps gradually, and it doesn't allow them to be entirely black. But unfortunately, with our project we ran into two problems. So the first of them is connected to the running average, right? Why do we use the running average? Why can't we just take a difference from when there is silence? So we have the amplitude when there is silence, and the amplitude of when there is song, where there is sound playing. Why can't we just take a difference between these two amplitudes and that's all? Well, as it turns out, when we change the lamps, the input from the microphone changes by a constant value. We do not know why this is, but we do know how to fight this problem. And we do it with a running average, which values the most recent inputs from the microphone. That's how we fight it. And you can see on the graph, the change that occurs. So another problem is we don't know the loudness of the song or how far the source of the sound is. And this is a problem because we use the variable max. What do we actually do with it? So we take the difference, we take the current difference, right, and we divide it by the variable max, which is supposedly the maximum difference that between the silence and the song amplitude. And so we divide these two variables and we get the percentage. And so this percentage, by this percentage, we set that amount of lamps alight. For like 20%, we set like 7 lamps alight or whatever. So how do you fight the problem of not knowing the maximum? We fight it by decreasing this maximum every second. So there is some initial value, then we decrease it every second. That's one thing that we do. And the other thing is if we encounter a bigger difference in the amplitude than the maximum was, then we update the maximum. So as you can see, the first graph shows the change, how it decreases over time, and the second graph shows how it gets changed by a bigger difference in the amplitude. Here's the code.
The mathematical part of our project, we were choosing the FHT, which stands for Fast Hartley Transform. The Hartley Transform could you remind of Fourier Transform. Both of them are integral transforms. So, but the Hartley transforms can transform the real value functions to real value functions. So, as you can see on this formula, this is a formula for Fourier transform, which has the imaginary part, and this is the Hartley transform formula, which doesn't have imaginary part. So why do we need it? We can basically, when we record the audio signal, we record it in time domain. Then, by using the special library in Arduino, we can we can basically transform from time domain to frequency domain to obtain the nice magnitude of each frequency in a time. And then we can implement it in our LED strip as the low frequencies, middle frequencies, and high frequencies. So that's all. Thank you for watching our video. Subscribe and put a like.